faithfully conveying value and interpreting great books worldwide. Hello, this is Sally's Book Talk. Today's book for interpretation is Big Science, subtitled Ernest Lawrence and the Military-Industrial Complex He Pioneered. When it comes to big science, what large-scale experimental projects are you familiar with? Feel free to share your thoughts on big science in the comment section. This book tells the story of a scientist named Ernest Lawrence and his invention called the cyclotron. The term military-industrial in the subtitle refers to Lawrence later applying his invention and research methods to major military projects, including atomic bomb development. And the author Michael Heltzik is a Pulitzer Prize-winning columnist whose works focus on major events in modern American history, like Colossus, about Hoover Dam's construction, and Iron Empires, about railroad tycoons' power struggles. He excels at unearthing historical materials and clearly mapping event developments to present vivid, detailed stories. Now, this big science does exactly that, and we'll break its story into three parts for this interpretation. First, let's explore what big science actually means. The second part will introduce who Lawrence was and how his invention relates to big science. The third part will focus on big science's contributions, especially its critical role in developing the atomic bomb. So, what exactly is big science? The term big science was coined by physicist Weinberg in 1961 as director of Oak Ridge National Laboratory. He distilled this concept while summarizing science's evolution. Per Weinberg and academia, big science refers to massive research projects requiring enormous financial and human resources. Such projects pursue grand scientific goals using expensive, complex equipment with cross-disciplinary expert collaboration. In recent years, the most iconic big science example is the Large Hadron Collider project. This massive device, abbreviated LHC, sits 90 meters underground on the France-Switzerland border. Its main structure is a 27-kilometer concrete tunnel housing 9,600 magnets. Scientists and engineers from over 80 countries participated in building the LHC, which took 25 years and cost $10 billion. The funding mainly came from the more than 20 member states of CERN. It truly deserves to be called the most complex scientific equipment on Earth. It's worth mentioning that our country was also a key participant in the LHC project, investing over 80 million yuan to build several critical detectors. In 2012, CERN announced the discovery of the Higgs boson particle using this super machine. It's one of the fundamental particles that make up the universe. The theory about this particle was proposed as early as 1964, but it wasn't until half a century later that it was finally observed with this device. Not just the LHC, but many well-known scientific projects like the atomic bomb development, America's moon landing program, and China's Fast Radio Telescope all fall under the category of big science.
Since there's big science, naturally there's also small science. Small science research relies more on scientists' inspiration and creativity.
They often achieve many theoretical or experimental breakthroughs using just some simple instruments. In fact, before the 20th century, scientists all worked in the small science mode. The most representative figure in small science is the famous physicist Rutherford, whose notable achievement was the discovery of the atomic nucleus. In this experiment, Rutherford used a small bottle containing some radioactive radium, which constantly emits alpha particles. Then he bombarded a small piece of gold foil with these alpha particles and used a special glass plate to observe their trajectories. The results showed that most particles passed through the foil with almost no change in trajectory, but about 1 in 8,000 particles deflected at large angles or even bounced back directly. And Rutherford explained this by saying that the inside of the atoms in the gold foil is mostly empty space, with almost all the mass concentrated in a tiny nucleus. When an alpha particle hits this nucleus by chance, it deflects or bounces back, and this nucleus is the atomic nucleus. This research greatly advanced our understanding of the atom's interior. And throughout the experiment, Rutherford had only two assistants helping him. For a long time, the small science research model dominated academia until Lawrence's emergence changed everything. Specifically, Lawrence and his invention of the cyclotron facilitated the transition of scientific research from small science to big science. In part two, we'll talk about what kind of person Lawrence was and how his invention relates to big science. In 1901, Lawrence was born in South Dakota in the U.S. Midwest. He was very independent from a young age. At 8 years old, he dared to travel alone to another city to visit his cousin. As a child, Lawrence had a slight stutter, but after consulting a doctor, it was found that this might be because his mind worked too fast for his speech to keep up. This minor issue disappeared in adulthood. Lawrence was also fascinated by the emerging radio technology of the time. He even drilled holes in the dining table to install a transmitter when his mother was away, and Boston were not. In 1925, at just 24 years old, Lawrence earned his PhD from Yale University. During his studies, with his talent and intellect in experiments, he quickly made a name for himself by publishing a series of high-level papers. Additionally, he actively participated in industrial research, spending 2 summers in General Electric's labs helping the company with technological improvements. In the spring of 1926, Professor Leonard from the University of California reviewed Lawrence's work and called him the most talented young experimentalist in the eastern U.S. This outstanding young scholar, Lawrence quickly attracted the attention of UC Berkeley. For convenience in interpretation, we'll simply refer to it as Berkeley from now on. Today, Berkeley consistently ranks among the top 10 universities globally and is undoubtedly a world-class institution. But in the 1920s, Berkeley had little fame. Although government funding and private donations ensured ample finances, there were no prominent scholars in its 1926 physics department. Only 2 young professors. So recruiting talents became Berkeley's main task. Well,
The university's talent recruitment strategy focused on finding young people with potential.
for example, they obtained the National Research Council's funding list for outstanding doctoral candidates and screened it for potential hires. Lawrence was on this list. To attract him, Berkeley offered a generous package with a $3,000 annual salary. In the 1920s in the U.S., the average worker's annual salary was just over $1,000, and the school guaranteed to reduce his teaching duties, giving him ample time for research. And Lawrence, in the early stages of his career, gladly accepted this offer. 2 years after being hired as an associate professor in physics in 1928, at just 29 years old, Lawrence was promoted to full professor, making him the youngest full professor at Berkeley at the time. Of course, Lawrence did not disappoint Berkeley's expectations. In 1929, he proposed a genius idea and successfully designed a device to accelerate particles. This is the famous cyclotron. Before understanding how this device works, we need to know why accelerating particles is important. The concept of particles is actually very broad. Tiny particles like ions and protons that physicists focus on can all be considered particles. After accelerating particles, they gain high energy, like a bullet. Using such high-energy particles to bombard materials often leads to new substances or phenomena. The higher the energy of particle acceleration, the more likely it is to achieve new breakthroughs. For example, in the atomic nucleus experiment mentioned earlier, radium emits alpha particles with an energy of about 7.6 million electron volts. And Rutherford once admitted that he wished he had a device capable of providing 10 million electron volts. However, in the process of continuously increasing particle acceleration energy, scientists and engineers encountered a bottleneck. To accelerate particles, they need to be in a strong electric field. But devices that generate large electric fields are often very unstable and frequently cause explosions. To obtain sufficient electric fields, some even thought of harnessing lightning. Three researchers from Berlin University set up a 600-meter steel cable in the mountains to capture lightning energy. And they succeeded in getting 15 million volts, but one was killed instantly by the lightning. Given these difficulties, if anyone could invent a method to stably accelerate particles, it would undoubtedly cause a sensation in academia. So Lawrence started thinking about this problem very early on, and his efforts paid off. In 1929, Lawrence happened to read an article and immediately gained inspiration. This article came from a German magazine called Archiv für Elektrotechnik. The author was a Norwegian physicist named Rolf, who proposed accelerating particles to high energy states not in one step, but through multiple electric pulses for gradual acceleration. It's somewhat like a multi-stage rocket design, accelerating particles step by step through multiple electric fields to achieve high velocity. The report was in German. Lawrence couldn't read the text, but just from the pictures and tables, he grasped the article's key points.
If you applied 1,000,000 volts to the device, it would easily explode.
But with this step-by-step design, you only need a few thousand volts on the equipment. Lawrence refined this concept further into a genius solution. In this design, Lawrence made circular tracks for the acceleration channel, applying a few thousand volts of acceleration voltage within the tracks. He also designed an external magnetic field to control particles along curved paths. The result was particles repeatedly accelerating through this circular device, gaining tremendous speed and energy. BAN. With this idea, Lawrence did preliminary calculations and brought in faculty colleagues to discuss feasibility. After confirmation from several colleagues, his idea was indeed promising. Practice is the sole criterion for testing truth. While Lawrence's design was sound, the crucial step was building a physical prototype. There was a perfect person for this job, Lawrence's student, Livingston. This student grew up on a farm, loved tinkering with machines, and often repaired complex lab equipment himself. In 1931, Lawrence and Livingston collaborated from scratch, building a 10-centimeter brass vacuum chamber with electromagnets to realize their particle acceleration scheme. Finally, in December that year, they successfully accelerated ionized hydrogen molecules 20 times using this device. Later, they borrowed stronger electromagnets from colleagues and accelerated deuterium ions to 80,000 electron volts. This was the world's first cyclotron. After proving this approach effective, the design and research of particle accelerators rapidly advanced. Lawrence's devices grew increasingly larger, from an initial 10 centimeters to 94 centimeters, then to 152 centimeters, achieving higher and higher particle acceleration energies. Rutherford's envisioned 10 million electron volts was easily surpassed. The 152-centimeter accelerator even reached 17 million electron volts. In 1940, Lawrence planned a 467-centimeter diameter particle accelerator to achieve the astonishing goal of 100 million electron volts. Through continuous refinement of the cyclotron, Lawrence's research team achieved a series of scientific breakthroughs. For instance, bombarding ordinary elements with high-energy accelerated particles could create radioactive isotopes. Isotopes are different forms of the same element. They share chemical properties but differ in mass and physical characteristics. Radioactive isotopes hold significant research value in fields like nuclear physics and medicine. By late 1939, over half of all artificially created radioactive isotopes came from Lawrence's team. Even cyclotron waste became priceless. In 1936, Lawrence removed metal strips from discarded equipment walls and gave them to a scholar named Segre. These strips had endured years of intense radiation. Segre discovered they were a treasure trove of radioactive materials.
He extracted isotopes like phosphorus and cobalt and even discovered an element never before found in nature.
This element, number 43, was named technetium, derived from the Greek word for artificial. These achievements made Lawrence's lab the world's premier physics play. Research sanctuary.
Centered around large cyclotrons, Lawrence built an interdisciplinary research team, establishing the big science model.
In developing this model, Lawrence pioneered new strategies for funding, personnel, and disciplinary development. First, funding was big science's greatest challenge. The initial 10-centimeter accelerator cost under $100, but expanding sizes demanded exponentially more resources. For example, when Lawrence planned to build the 467-centimeter accelerator, its budget reached a staggering $1 million. Additionally, another $500,000 was needed for 10 years of maintenance. Not to mention, the machine required a 4,500-ton supermagnet to operate, far beyond what university and government funding could cover. So while other scientists focused on lab research, Lawrence traveled seeking funds. A key skill of his was persuading diverse sponsors. Lab sponsors were mainly charitable foundations or independent investors. For backers from different industries, Lawrence tailored his pitch to show how cyclotrons could benefit their fields. And for biomedical organizations, he demonstrated how accelerators could mass-produce radioactive isotopes to kill cancer cells.
To entrepreneur investors, he convinced them nuclear power could provide limitless energy and huge profits.
For charitable foundations, Lawrence emphasized the accelerator's essential role in frontier physics exploration. Sponsoring his research would immortalize foundations in history. Lawrence's crowning fundraising achievement was persuading 19 Rockefeller Foundation trustees in 1940 to contribute $1.15 for the 467-centimeter cyclotron. Before this, no single lab had ever received such a large donation. In talent management, Lawrence excelled at organizing interdisciplinary teams. First, he was highly charismatic, friendly, enthusiastic, and able to connect with everyone. An early graduate student recalled Lawrence voluntarily helping with late-night experiments. As a leader, Lawrence fought for his team's benefits. When Harvard tried to poach him with generous offers, Berkeley countered, and Lawrence negotiated increased funding for a director, assistant, 2 associates, and a researcher. To retain Lawrence, Berkeley ultimately agreed to this plan. These positions successfully accommodated a group of outstanding scholars in the lab at that time. More importantly, Lawrence possessed broad scientific vision to explore the cyclotron's applications across fields. Lawrence's brother was a medical expert. It was Lawrence who pulled him into the research team, enabling subsequent medical applications of radioactive elements. At its peak, Lawrence's lab had 60 scientists and over a dozen technicians working simultaneously, from physics, chemistry, medical engineering, and more. As the author notes, this team was practically like an army. Lawrence excelled not just at fundraising and talent development. He devoted his life to advancing the entire discipline. He never kept his cyclotron invention secret, instead actively promoting its adoption. Lawrence was incredibly generous to universities and companies seeking help. He produced radiation sources for doctors' cancer treatments. The lab even provided other universities with free cyclotron blueprints. By 1939, nearly 20 physicists trained on Lawrence's machines were building cyclotrons at universities worldwide. In 1935, when the university-built cyclotron malfunctioned, Lawrence immediately sent top experts for on-site guidance.
This open, inclusive attitude earned Lawrence stellar repute in academia and industry.
Every year, scholars came to Berkeley without pay just to collaborate with Lawrence's team. This fostered rich cross-field exchange and accelerated cyclotron research development. Suddenly, Lawrence became hugely famous. In November 1937, he appeared on Time magazine's cover at 36. He was among America's most renowned scientists. And in 1939, unsurprisingly, Lawrence won the Nobel Prize in Physics for inventing the cyclotron. Later, 7 of his students and colleagues also won Nobel Prizes in physics or chemistry. Thus, through genius, intellect, exceptional leadership, and immense contributions to science, Lawrence achieved the highest honors possible for a scientist. The big science model he pioneered, relying on large-scale equipment and interdisciplinary teams, has indeed greatly accelerated scientific progress. In Part 3, we'll explore big science's contributions during World War II, especially its critical role in developing the atomic bomb. First, some historical context. In 1939, Nazi Germany invaded Poland, marking 101's full outbreak. Simultaneously, physics experienced major breakthroughs. In 1938, European scientists, including Meitner, discovered nuclear fission. Simply put, a heavy atom hit by neutrons splits into smaller atoms, releasing more neutrons. Physicist Fermi's team then designed a nuclear reactor confirming chain reactions in fission. Take uranium, the most common fission element, as an example. A chain reaction occurs when uranium releases 2 to 4 neutrons after splitting, which then strike nearby atoms, causing cascading fission. During nuclear fission and chain reactions, atomic mass converts to energy. Per Einstein's mass-energy equivalence theory, this energy release is colossal. If weaponized, this could surpass any existing weapon's destructive power. Reports suggested Germany was already researching this, leaving the Allies little time. The situation was critical. In late July 1939, Einstein and other scientists co-signed a letter to President Roosevelt. It emphasized this new bomb's potential. It warned German scientists might be ahead, prompting Roosevelt to immediately order beating Hitler to the bomb. To build this superweapon, the key requirement was obtaining sufficient uranium. Uranium has 3 natural isotopes. Only uranium-235 can fuel nuclear fission. But uranium-35 VENICE constitutes just 0.7% of natural uranium. Scholars estimated a bomb required tens of kilograms. The Hiroshima atomic bomb later used a staggering 45 kilograms of uranium-35. To meet this massive demand, the military and scientists adopted a multi-pronged strategy, pursuing 4 enrichment methods simultaneously, with competing teams to maximize output. All 4 methods were still in the experimental exploration phase. No one could be certain which would actually achieve large-scale production.
They were gaseous diffusion, thermal diffusion, high-speed centrifugation, and Lorenz's electromagnetic separation method.
Electromagnetic separation exploited uranium isotopes' slight weight differences. Heavier particles follow different magnetic paths for separation. This method fundamentally resembled particle accelerators. To validate feasibility, Lawrence had his team test on their accelerator, quickly isolating trace uranium-35 by 23 from natural uranium, proving the theory. Now it was up to Lawrence to scale up production. He mobilized the big science model again, coordinating personnel, funding, and equipment. Personnel-wise, Lawrence reassigned his best researchers and engineers from the 467-centimeter cyclotron to develop uranium-25 electromagnetic separators. Well, where else is this? Meanwhile, his long-built network kicked into gear. Cyclotron researchers nationwide rushed to assist Lawrence. They included scholars from Princeton, Washington University, and R&D staff from companies like General Electric. For funding, the lab quietly diverted $5,000 from other grants to modify machines, like building a new vacuum chamber. Though unconventional, wartime urgency forced the team forward, but funding issues resolved quickly. With preliminary results, Lawrence secured a $400,000 military grant, dramatically easing their budget. With people and funds, Lawrence's team developed a separator shaped like a C with isotope collectors for uranium-253 extraction. Lawrence called this device the calitron. Throughout summer 1942, researchers refined the calitron using techniques from cyclotron construction. With the calitron device, electromagnetic separation efficiency far surpassed other methods. By January 1943, the lab could produce 18 micrograms of enriched uranium in 9 hours. Though the uranium-35 sample weighed just 1,000th of a sand grain, its fissile isotope concentration was 34 times natural uranium's. To boost efficiency further, Lawrence made an all-or-nothing decision, sacrificing the planned 4,500-ton cyclotron by donating its custom 4,500-ton magnet to power the calitron. He also converted the accelerator's reserved space into an electrical equipment production facility, plunging the team into wartime urgency. Experts and staff worked 3 shifts around the clock to keep equipment running 24/7. After this gamble, Lawrence confidently reported producing 100 grams of enriched uranium daily, leaving competitors far behind. Ugh, ugh. Government and military leaders recognized his efforts, entrusting Lawrence with designing a full-scale uranium enrichment plant. Codenamed Y-12, this plant covered 334 hectares in Tennessee's southeastern river basin. Monumental logistics. Construction required 128 rail cars of electrical equipment, 63 of concrete, and over 1,500 truckloads of timber. The enriched uranium in the Hiroshima Little Boy atomic bomb, dropped on August 6, 1945, came from Lawrence's Y-12 plant. Notably, in 1940, scientists produced a new element using the 152-centimeter accelerator. This element, number 94 on the periodic table, was named plutonium, far more fissile than uranium-235 and easier to weaponize. The Nagasaki atomic bomb used a plutonium core. Undoubtedly, Lawrence and the cyclotron played pivotal roles in atomic bomb development. From designing the 10-centimeter cyclotron, to leading interdisciplinary teams, to directing massive uranium production, his journey defined big science. Throughout these events, Lawrence demonstrated a scientist's spirit of exploration, a leader's coordination skills, and a visionary's foresight. Lawrence's invention of the cyclotron advanced physics, and his big science model promoted progress across academia. To honor Lawrence's contributions, his Berkeley lab was later named Lawrence Berkeley National Laboratory. Finally, let's discuss the lasting impact of big science. Lawrence's big science approach has now become mainstream in academia. The most important research projects in major tech nations rely on interdisciplinary teams, large-scale equipment, and massive funding. Today's scientists aren't just focused on experiments. They invest much effort in securing funding and managing teams. The book's author humorously notes that research leaders today must be not only scientists, but also bosses. Cheerleaders and salespeople, of course. Small science methods haven't disappeared. With clever minds and simple equipment, scholars still produce excellent research. Whether big science or small science, both contribute to humanity's exploration of the unknown. Do you have similar experiences or stories to share from participating in research projects? Feel free to leave comments below. All right, that's our interpretation of big science. Notes are below the audio. See you next time.